Okay, proof. We will use mathematical induction. So let P sub n be the statement that the interior of the intersection from I equals 1 to n of the sets A sub I is equal to the intersection from I equals 1 to n of the interiors of those sets. Then P sub 1 is the statement that the interior of A sub 1 is equal to the interior of A sub 1, which is true. So now suppose that the statement P of n minus 1 is true. That is, the interior of the intersection from I equals 1 to n minus 1 of the sets A sub I is equal to the intersection from I equals 1 to n minus 1 of the interiors of those sets. Then the interior of the intersection from I equals 1 to n of the sets A sub I is the interior of the intersection of two sets. The intersection of the intersection from I equals 1 to n minus 1 of the sets A sub I with A sub n. Now by the previous lemma, this is equal to the intersection of the two sets, or rather this is equal to the intersection of the interior of the two sets, and so we have the intersection of the interior of the intersection from I equals 1 to n minus 1 of the sets A sub I with the interior of the set A sub n. Now by the induction hypothesis, this the interior of the intersection from I equals 1 to n minus 1 is the intersection from I equals 1 to n minus 1 of the interiors of the sets A sub I. And so this is equal to the interior, the intersection from I equals 1 to n of the interiors of the sets A sub I. And so the case, or the statement P n minus 1 implies the statement P of n. Therefore, by induction, we have that the interior of a finite intersection, intersection from I equals 1 to n of sets A sub I is equal to the intersection from I equals 1 to n of the interiors of the sets A sub I for any positive integer n. Okay, second statement. Let P sub n be the statement that the closure of the finite union from I equals 1 to n of the sets A sub I is equal to the union from I equals 1 to n of the closures of the sets A sub I. Then the statement P sub 1, or P of 1, is the statement that the closure of A sub 1 is equal to the closure of A sub 1, which is true. So now suppose that the statement P of n minus 1 is true. That is, the closure of the union from I equals 1 to n minus 1 of the sets A sub I is equal to the union from I equals 1 to n minus 1 of the closures of the sets A sub I. Then the closure of the union from I equals 1 to n of the sets A sub I is the closure of two sets, or rather the closure of the union of two sets. the union from I equals 1 to n minus 1 of the sets a sub I with a sub n. Once again, by the previous lemma, this is the union of the closures of these two sets, and so this is the union of the closure of the union from I equals 1 to n minus 1 of a sub I with the closure of a sub n. Now, by the induction hypothesis, the closure of the union from I equals 1 to n minus 1 of the sets a sub I is the union from I equals 1 to n minus 1 of the closures of the sets a sub I. And so this is equal to the union from I equals 1 to n minus 1, from I equals 1 to n of the closures of the sets a sub I. And so the statement P of n minus 1 implies statement P of n. Therefore, by induction, we have the closure of the union from I equals 1 to n of sets a sub I is equal to the union from I equals 1 to n of the closures of those sets, and this is for any positive integer n. Okay, so now we'll look at some properties of the digital line. Now recall that in a topological space, which we'll call X, where the cardinality of that underlying set is greater than or equal to 2, a point X in the space X is an isolated point if and only if the singleton which contains that point is open, so next we'll show that every odd integer is an isolated point of the digital line. So proof. Notice that for every odd integer, the singleton containing that odd integer is open, as it is a basic open set. That is a basic, or rather a basis element, a basic open set. So as the cardinality of the underlying set, that is the cardinality of the integers, is greater than 2, we have that every odd integer is an isolated point of the digital line. Okay? So next, we will show that every even integer is a cluster point of the digital line. So proof. Let n be an even integer. Then, for every open neighborhood, u of n, the basis element, b sub n, which is the 3-point set, n minus 1, n, and n plus 1, must be a subset of the neighborhood U. And so the 2-point set n minus 1, n plus 1 is a subset of the intersection of the set U with the complement of the singleton containing the point n in the digital line. That is, for every open neighborhood U of n, the intersection of that open neighborhood with the complement of the singleton containing the point n is not empty, and hence every even integer is a cluster point of the digital line. Okay? So recall that in a topological space, a point is either a cluster point or an isolated point, but not both. So the set of all isolated points of the digital line is the set O of all odd integers and the set of all cluster points which, remember, is the derived set is the set of all even integers, the set E of all even integers. And hence the number of isolated points of the digital line is the cardinality of the set of odd integers, which we have demonstrated is Aleph null. It is a countable set. That is, there is not only countable, but countably infinite. So there is a countably infinite number of isolated points in the digital line. Now recall that subsets of a nowhere dense set are themselves nowhere dense. So every subset of the set of even integers is nowhere dense. In particular, every singleton containing an even integer is nowhere dense in the digital line. So next, we will show that every singleton containing an even integer is closed but not open further. It is its own boundary. So proof. Let M be an even integer, and let the set script B sub E be the set of all basis elements B sub n, where n is even, so denote the set of all integers greater than or equal to m plus 1 using interval notation. Then this set is a union of the elements in the collection script B sub E. Notice that the odd integer m plus 1 is in the basis element containing the 3 points, or the 3 integers, m plus 1, m plus 2, m plus 3. So this is the basis element for the even integer, m plus 2. We continue the union with the next even integer, which is m plus 4. And so it is the 3-point set, m plus 3, m plus 4, m plus 5, and so on. Notice that we will always have an overlap between 2 consecutive even integers. And so this is the union for n greater than m of the elements B sub n, where B sub n is in the set script B sub E, that is even, or rather the basis elements for even integers greater than m. And so this set is open, as it is a union of basis elements. Similarly, the set of all integers less than or equal to m minus 1 is open, since this set is a union for all n less than m of the elements B sub n, where B sub n is in the collection script B sub E. And so the complement of the singleton containing the even integer n is the union of these sets, and is therefore open, and hence the singleton containing the even integer is closed, as its complement is open. And so it is its own closure. Now, as the singleton containing an even integer is nowhere dense, we have that the interior of the closure of this set is the interior of the singleton, which is empty. And so the singleton is not open since it is not equal to its interior. And the boundary of the singleton is the closure of the singleton, set minus the interior, which is the singleton, set minus the empty set, and so is the singleton. And so the singleton set containing an even integer is its own boundary.